Light, one of the most fundamental yet complex things in the universe. What exactly is light? Let me enlighten you. By the late 19th century, experiments are established that light was a form of energy that traveled as waves. Like if you accelerate water particles, they produce water waves. And if you accelerate massive bodies in space, they produce gravitational waves. Similarly, if you accelerate charged particles, they produce electromagnetic waves, which is light. In the 1900s, however, Max Planck proposed the idea of quantization. Look, I can stand on this step and this one, but not anywhere in between. The height of each step is the smallest discrete quantity or a quantum by which I can move up or down. Similarly, Planck proposed that light also comes in quantum or discrete tiny packets of energy. We now know that these are elementary particles with zero mass and zero charge and are called photons. So, is light a particle or a wave? Or is it both? Let me explain. Observe the two shadows of a cylindrical object. Just from the shadow, one might think the actual object to be a circle or a rectangle depending on how it was held. But the cylinder in itself is a much more complex object. It's a similar thing for light. It's that it's neither a particle nor a wave, but behaves both as a particle and a wave simultaneously, and one characteristic dominates over the other depending on the situation. Can light have momentum? Turns out, from special relativity, we get this equation for the total energy of a body. Note how for a body at rest, the same equation gives the famous E equals mc square. For a photon which is massless, we see that its momentum equals its energy divided by its speed. There's energy for sure, which is why these plants are able to manufacture their food and also why we feel hot when recording out in the sun. Therefore, from this relation, we can see that light has momentum. And boom! From Sir Newton's second law, we can see that when light falls on an object, it exerts a force on it, and that's the force behind radiation pressure. We can use this force of light for accelerating light sails in space by shining a powerful beam of light at them or simply using radiation pressure from the sun. In space, over long periods of time, as the photons transfer the momentum onto the sail may reach speeds up to 10% the speed of light without any fuel. Of course, this is just one application of radiation pressure, and the list is much longer. Radiation pressure also prevents highly massive stars from collapsing under their own force of gravity. Light having momentum is in fact so fundamental to physics that one of the most successful theories ever, quantum electrodynamics, describes the interaction between particles in terms of exchange of photons instead of relying on classical force fields. For example, when two electrons come close, according to QED, they exchange virtual photons. The exchange of momentum and energy is what causes the electrons to repel. When Kepler discovered that it was radiation pressure that was causing the tails of comets to always face away from the sun, what he didn't know was that the same discovery might one day be responsible for some of humanity's greatest advancements. Thanks for watching.